Welcome to part 5 of the series of data fitting, and in this part we look at special models. These include logarithmic, power, sigmoidal, Gaussian, and sinusoidal functions. Logarithmic models are the opposite of exponentials. The equation used is y equals a times the natural log of x plus c. These create curves that rise quickly at first, then they level off, and that shows like diminishing returns. And there are many examples of this, but I can mention to you learning curves. Learning curves because you will often learn very quickly at the beginning, and then the learning will decrease with time because you get more exposure to different examples. So your learning will go very fast at the beginning. And the same thing with sound intensity. And this is what is often measured, or is always measured, in decibels. We use logarithmic models when, like we mentioned before, when there is an increase in x, produce smaller and a smaller increase in y. So to make this clearer to you, watch how the curve shoots up quickly at the beginning, then gradually flattens out. This describes many natural phenomena where it diminish over time. Power models have the form or the equation y equals a times x to the power of n. And in this case, n can be any number, not just an integer. These are similar to polynomials, but they are more flexible. The power equation follows this format: y equals a times x to the n. So when n is less than 1, like for example you get a square root, you get diminishing returns. So what happens here, the curve rises quickly, then it flattens. When n equals to 1, it's just a linear, so it forms a straight line. When n is greater than 1, like x squared, then you will get accelerating curves. Just to have an idea about what kind of examples here, you can look at the allometric growth in biology and many physics laws. The Richter scale is logarithmic. So this scale is the one which is used to calculate or measure the severity of earthquakes. So the magnitude equals a log base, so it's a logarithmic as we mentioned, log base of 10 of a over a naught. So each whole number here increase represents 10 times more ground shaking amplitude. So we use the logarithmic scale here when we're dealing with huge ranges. So it makes comparisons much easier. The same principle applies to pH calculation or pH measurements of acidity of acids and bases. And likewise, it's used for sounds for when measuring using decibels. In pharmacology applications, the dose response curves follow this similar equation, which is effect equals E max times D divided by the quantity ED50 plus D. So the ED50 is the dose producing 50% of the maximum effect. If you plot this on a log dose scale to see the full curve as you can be seen here, the therapeutic index is TD50 divided by ED50, which implies a higher value means a safer drug with more room or more options between effective and toxic doses. In rheology, we use the power law, and in this case n is the flow behavior index. So if n equals 1, then we call that Newtonian. So that means it's a constant viscosity, just like water. If n is less than 1, it's shear thinning. It's called shear thinning. So viscosity basically decreases under shear, just like most creams and lotions. And if n is greater than 1, we call that shear thickening, just like when you get cornstarch in water. So understanding this is key for formulation science, because these often are described commonly by rheology. So because those products, they have different flow properties. Sigmoidal or logistic models create S-shaped curves. They start flat and they rise steeply in the middle, then they level off at a maximum. This shape appears whenever there is a constrained growth. So unlimited at first, so it will just go fast and fast. Then because of this constraint, it will be limited by resources. The logistic equation can be expressed as y equals L divided by the quantity 1 plus E to the minus k times the quantity x minus x naught. So in this case, L is the carrying capacity. So basically this is the maximum value. K controls how steep the transition is, and x naught is the inflection point. So basically this is the point where the curve is the steepest. So I can give you some examples on this. For example, is adoption curves, dose, or maybe something like dose response, so often approximated by logistic or Hill type models. And also population limits, or all of those are examples of logistic equations. So the population growth follows P equals L divided by the quantity 1 plus E to the minus K times the quantity T minus T naught. So L is the carrying capacity, and this is, in this case, is the maximum population. So the curve has three phases: lag phase at the start, and then log phase where the growth is rapid, and stationary phase where the population levels off. So the inflection here occurs at exactly P equals L over 2. So the same pattern applies. This kind of trend or pattern also applies to technology adoption. So that basically means when there's a new technology, it's going to follow this kind of similar trend to population growth, and there will be a limit for unlimited growth. Let me give you another example here on dissolution of pharmaceuticals. So in this case, we have a drug dissolution from tablets, and that often follows sigmoidal kinetics. And here we represent this as percentage dissolved, and the way you express that as the percentage dissolved equals 100 divided by the quantity 1 plus E to the minus K times the quantity T minus T50. The T50 is the time for 50% release. So you can compare, for example, immediate release versus sustained release formulations. It could be British pharmacopoeia or the US pharmacopoeia. In this case, they will provide some specifications. So they will provide, for example, require the Q value, that is the percentage dissolved, to be at least 80% within 30 minutes for immediate release products. Hence, we need to know, if we don't understand what's going to happen, or we don't know the shape of our profile, we will not be able to accurately calculate the amount that is released. Another shape often seen is in DSC is the glass transition, which shows the step change in heat capacity, basically when a material is heated and it transforms from glass to rubber, and that is the glass transition temperature. We report three values, as you can see in the curve: onset, midpoint, and endpoint. Tg values. The midpoint is the most common. So well, there is something called plasticizers, and those the classical one is water, because water exists is the moisture content, and generally speaking, as a rule of thumb, for each 1% of moisture, the drop in glass transition is approximately 10 degrees. So that helps. If we know this, if we estimate the glass transition temperature, then we will know how much impact it will have in terms on the drop of its glass transition, because this goes into the stability of materials. So there is probably beyond the scope of this topic, but generally speaking, just for you to know, the shape of this phenomena of the glass transition temperature is described using the sigmoidal function. The Gaussian or normal distribution is the famous bell curve. So you will see it's symmetric with tails extending outward. It is classically describes natural variation, things like heights, measurements errors, and many biological parameters. The Gaussian equation equals A, or can be described as y equals A times e to the minus the quantity of x minus mu squared divided by 2 sigma squared. In this case, mu is the mean value, so it's basically the center of the peak. Sigma is the standard deviation, i.e. the width. A is the height or the amplitude. So as mentioned before, the examples include of this: measurements error, it could be peak fittings, and can also included in statistics, many applications in statistics. So just to explain this more practically, human height follows a normal bell curve distribution. About 68% of values fall within plus or minus 1 sigma of the mean. About 95% fall within plus or minus 2 sigma values. This same distribution described measurement precision. So if your balance has sigma of 0.001 grams, that means 95% of readings will be within 0.002 grams of the true value. Another application is chromatographic peaks seen in HPLC, high performance liquid chromatography. So these follow or almost follow approximately Gaussian shaped curves. The retention time TR is the center of the peak. Sigma relates to the peak width, and the area under the peak is proportional to the concentration. And this is how we quantify the amount of for example, a drug or compound or whatever you are testing. So fitting Gaussian curves allows accurate quantification, even when sometimes peaks partially overlap. Let's look at this another example taken from DSC, differential scanning calorimetry, and in this case melting phenomena. It's called melting endotherm, and these are often approximately Gaussian, and it can be fit with Gaussian functions. Tm, which is the melting temperature, gives you the peak position. Delta HF is the enthalpy of fusion, and it comes from the peak area or area under the peak. Sharp peak indicates high purity. Impurities often will broaden the peak. You can then calculate the percentage of crystallinity by comparing the fully crystalline reference material. So fully crystalline reference material 100%, and anything compared to that will be a fraction of it. Sinusoidal models describe oscillating patterns. So the equation used to describe this kind of pattern is y equals a times sine sine of the quantity B, x plus c plus d. And A is the amplitude, that is the height of the wave. B, it will tell you the frequency, so how many waves you will have, and basically how often they repeat. C is the phase shift, and D is the vertical offset. And to give you an example of those, some of them very common is the seasons changing, like winter, summer, spring. I'll show you some example later on. Tides, circadian rhythm, and vibrations. Watch this seasonal pattern. So temperature rises and falls throughout the year in a regular wave pattern. Sine waves are periodic, as you can see here, so they repeat forever. The period is 2 pi divided by b. These appear in anything cyclic, so things like we mentioned, tides, season, circadian rhythm, mechanical vibrations. Tides follow sinusoidal patterns. H equals A times sine of the quantity B, T, plus C plus D. The period is approximately 12.4 hours. So that is how long between high tides. So A is the amplitude or tidal range. Fitting historical data lets you predict future tides. So essential for navigation and coastal engineering. The same mathematics describes seasonal temperature changes and circadian rhythms. Just here we have another example which is based on dynamic mechanical thermal analysis. And this kind of analysis, it applies oscillating strain, and it will then measure the stress response. So for purely elastic materials, stress and strain are in phase. So basically they peak together. The phase lag delta tells you the balance. So 0 degrees means elastic, or if it's 90 degrees means it's viscous. G prime, the storage modulus, represents the elastic behavior. G double prime, the loss modulus, represents the viscous behavior. And this is how we characterize materials like polymers, gels, and semi-solids.